All right, coming in.
I work for United Power. Me and a few co-workers have put together this high voltage demonstration trailer to show you guys the dangers of high voltage and the damage it can do. 10 years ago, I was electrocuted working in an underground switch cabinet like this here. Normally, the bottom of this cabinet is dead, the top is energized. We crossed the conduit, we didn't mark in and out, so when we energized it, the bottom became hot. My mind was elsewhere. I was thinking about going camping and four-wheeling. I did not check voltage, I didn't have ground, I didn't test. I reached in the bottom of this cabinet when I saw a loose bolt and I went to tighten it. And I took 7,200 volts to ground at my hand and wrist. These are the clothes that I was wearing the day that I was burnt. Wow. This is the FR shirt that I was wearing, the 100% cotton shirt that I was wearing, and the jeans that I'm wearing. This is before FR was required, but they were heavy-duty Carhartt double knee jeans. If it wasn't for these free pair of safety glasses that they hand out to us, my eyes would have been burned out and I wouldn't be here to tell this story. No reason to not wear your safety glasses. So after I made contact, I wasn't breathing, heart wasn't beating. My crew came over, drugged me away, and started to do CPR. Another crew member ran over and called Mayday, and within 15 minutes, Flight for Life was there. My crew did CPR, they got me going again, and saved my life. These are the gloves that we wear to protect us from the high voltage. We test these gloves every time before each use and send them in to get tested once a month. If I would have wore these gloves that day, this accident would not have happened. Same with this tester. We use these testers as a lifeline. Check for voltage anytime. If I would have used this, same thing. This accident could have been avoided. This part of the demonstration is to show when a person makes contact with high voltage. We have a hot dog for a finger, we use a cantaloupe for a head, and we use an orange to simulate your internal organs. The hard hat is for accidental contact. With our PPE, we're able to do this job safely. Work the overhead power lines and the bucket trucks, wearing rubber gloves and sleeves safely, and working on the ground wearing our PPE. We're able to do our job safely and go home every night.
What's gonna happen?
We use this vehicle here to simulate a dump truck or a piece of heavy equipment making contact with high voltage power lines. We like to show what we call step potential and how we want you to stay in the equipment if you can, or if you're in danger of fire or anything else, how to get out safely. Step potential is like throwing a rock in the pond. It's the voltage dissipating from the equipment. If you're in the equipment and you're in danger, we want you to jump out. We do not want you to step out. If you have a hand on the handle, a foot on the fuel tank, and you touch the ground with your foot, you're making contact, 7,200 volts to ground. That's lethal. If you have
Uh-oh.
we want you to hop away as far as you can, as safely as you can. If you can stay in the vehicle, stay in until we can get there and verify that it's dead and safe to get out.
Yeah, pretty good video.
Yep.
Went over a lot of stuff. Anything that you'd like to add there, Timothy?
Well, I didn't really like it, but it was the only fire retardant suit video that wasn't like 20 minutes long. But he didn't really talk a whole lot about it, but his suit was tore up. If he wouldn't have had it on, it'd have burned him all up instead of just losing his hand.
Yeah, you'll notice that there was a lot of charring and what do you call it? Ripping and tearing. Probably a pretty good explosion right there. But the big thing was it didn't catch on fire. There, it extinguished itself. There was no flames to it. So that probably helped him out a good bit.
He said something about 100% cotton shirt up under his suit.
That's correct.
Is what he had on.
That's what everybody should wear while you're out there. And don't wear any kind of polyester. 100% cotton socks, underwear, and t-shirts. They do actually have what they call a flame retardant rating to them. So those won't catch fire either. I mean, what about some other stuff he was talking about, especially there in the beginning? I mean, was it preventable?
Yeah, preventable.
Yeah. And what things could he have done to have prevented it?
Left that loose bolt alone.
Yeah. He did state a couple things there.
Check to see if there was any power on it.
Right. Javier, that's the first thing that you're going to be doing out there. And they have testers for this. All right, testers.
Wear insulated gloves.
Well, testers that you can put on the end of the stick to see if there's a presence of voltage. That's the first thing you're going to do whenever you approach anything, regardless, secondary voltages, primary voltages, whatever. Wear all the correct safety equipment. Now, rubber gloves. I mean, it's kind of, to me, Professor V, it's a head shaker.
Right.
You just don't stick your hand into something unless, one, you've tested it, two, you've grounded it, and then you have your protective gear on.
Right.
Okay. But we've been doing this a long time. So guys, never approach something, even if somebody says, hey, that switch gear over there, it's okay to go ahead and start work on it. What do you need to do first? Test, ground, make sure you got your protective gear on. Okay. Why did we not ground it first, then test it?
You might ground it wrong.
Well, give me a little bit more explanation of ground it wrong.
I don't really know.
Okay. You might be working and getting ready to ground something that's already energized or is energized. And if you do that, then you're going to get a big explosion in your face. If you test it for the presence of voltage and your tester says no voltage or doesn't give you an alarm, then you can ground it. Okay. Test, ground, then start your work. Professor V, anything you'd like to add there?
Yeah, what you just said, just want to, I'll piggyback on that part of it. There's been many an accident avoided because of the testers out there, because you stick your tester on and people thought it was dead. I've been to certain situations where had a live wire laying on the ground and it's just sitting there, 13,200 volts, just sitting on the ground, not arcing, not doing anything. And in my mind, I'm thinking, oh, this thing's dead. But then my training kicks in and says, get your tester out, check it first. And lo and behold, I've got 13,200 volts laying on the ground hot. You would think that it would knock something out if it would, be arcing and jumping and like what you see in movies or whatever, but that's not the case. Depends on your conditions outside. This was in a very sandy place, so it was like sitting on top of an insulator. So you never, ever, ever want to take somebody else's word for it. If it's just like what I'm saying, if it's just sitting there, guys, grab that tester. It could save your life. It may save somebody else's life. So be very careful with that kind of thing. And don't assume, because if you go up to a certain situation and there's a line on the ground and somebody said, oh, that's telephone, don't trust it.
Right. Yeah, Professor V brought something up there. So you've got an energized power line that falls to the ground, and he said it's laying in sand. Well, why is sand an insulator?
That's what glass
It has
is made
metal in
of.
it, don't it?
Logan Dennis, you hit the nail on the head right there. Glass is made from sand. Sand is a very good insulator in comparison to other soils that are out there, even asphalt and concrete. Sand will insulate pretty well. Okay, so we're moving down the body, and we had a couple of hints here this morning. Who wants to take the next safety meeting? I'll give you the subject. Good job, by the way, Timothy.
I'll do it, Mr. Shoemaker.
All right, Mr. Hunter Strong, rubber gloves.
Yes, sir. I
Line
got
up,
that ready.
line up
morning.
rubber gloves, and you will see plenty there on the internet as far as those are concerned for videos and whatnot. So you're tomorrow morning, safety meeting guy, Hunter Strong, rubber gloves.
Yes, sir.
Okay. Well, how was everybody's weekend?
It was good. How about yours?
It was good. What'd you do on your day off? Keep
I
it
stayed
clean.
home.
Stayed home. No fishing, no hunting, no nothing.
Oh,
Fishing.
Okay. Okay.
I went and saw my grandma. That's about it.
Well, good.
There you go.
Grandma needs love too.
That's right.
I hear you.
Here's my
Awesome.
office, Steve.
So we are getting ready to, Professor V, I haven't brought it up yet. We're
Go ahead.
getting to wrap up ELW 110. So we will be reviewing the exam today.
Oh, wow.
And yep, it's looking like tomorrow morning we'll go ahead and do you want to do that this afternoon or tomorrow morning? Professor V?
I'd say let's do it tomorrow morning.
Okay. And let you guys know, exams are comprehensive based on previous tests. So you're not going to see anything new, anything that should not be something you have seen before. How many questions is it, V?
It's only 4 questions.
4 questions. Now, there's a lot of thought processes in those 4
Sure
questions.
is.
You got to use your head, but there's only 4 questions on it. And we'll review that here in just a moment. Well, I have got my crew, and Professor B, you've got yours here together. I
Yeah.
will let you know, I'll be texting some people here during the course of the class that after our Zoom meeting today, I need to meet with you. I've got 1, 2, 3, 4. Got 4 people in my classroom that will not pass ELW 110, even with the exam. I would hope that you people know that you are who you are. Do realize that you have to have all 6 courses completed to get your certificate. There is, as far as college rules are concerned, you can return next semester if there are seats available to make up this course. I can tell you right now, there's no seats available. So I will call you off to the side after the meeting today, and let's see if we can get a game plan to get those 4 people taken care of.
I have 2 as well.
All right, so we'll discuss that after our meeting today, privately with individuals, not in front of the group and not side by side with somebody else. And let's see if we can get a game plan to go ahead and get all you guys caught up on the work that you have. Tristan,
Yes, sir.
what was the program? Brightspace what? Brightspace Pulse, I believe it was.
Yeah.
Okay.
Yes, sir.
All right, so there's an app out there, and it looked like it was pretty easy to use. There's an app called Brightspace Pulse. You can download that to your device, and you can see the grades that you have for the 4 quizzes you have taken thus far. Even if I've got a couple that haven't taken quizzes, period. So take those grades that you have, average them, and it'll let you know where you're at. While we're talking about grading system, A is 100 to 90, B is 90 to 80. C is 80 to 70. C is 80 to 70. D is 70 to 60. This is a certificate course. D is not a passing grade. Okay. D will not pass you through this course. So 70 to 60, you need to be above a 70 to be able to get this course completed, 70 or above. And of course, 60 to 50 would be an F. Any questions there? And like I say, don't point yourself out. If you need to send something to me on Remind, I just want to make sure everybody, we did that in orientation, got the grading system. A D will not pass any course in this program. Okay, Professor V, we want to jump right into the exam review?
Well, do you think maybe we need to go through quiz 4?
Yes, we already discussed that. That is excellent. Do you want to do that? Or you want me to do
I
that?
can.
Okay.
I've got my copy right here. If you want to maybe pull up your Wacom.
I will stand by.
I think this will be a help toward the exam.
Correct. Stand by 1 second.
Guys, I mean, I know there's some that did poorly on quiz 4. And we say it every time before a quiz, and we're going to start weaning you off that, that help, if you're not asking for it. So if you're not getting it, you need to ask, okay? Let us know you're not getting it, what part you're not getting. And I mean, it's nothing to be ashamed of. It's in the learning process. Everybody doesn't learn the same. So if you need help, that's what we're here for.
And in the afternoons is private.
Yeah.
Yeah, it's between you and me and Professor V. So, and I have to admit, the ones that have taken advantage of and come in the afternoon and have had questions about the questions, those are the hundreds in the 90 pluses that we see in our grades. You could be there if you want to. I mean, if you take the responsibility to get that grade, some of them are as simple as 10 or 15 minutes.
Yeah.
So we're here. That's all I can say. We're here for you.
Yeah,
Right,
I know. Yeah, I know a couple of them have helped, or we've helped, that the light bulb kind of goes off after we kind of explain things. We're not going to give you the answers right off, at all. We want you to figure it out. Then it's just kind of like an epiphany, boom.
Right.
It kind of clicks with you. So
yeah,
that's where we're trying to get, where you get that understanding.
Right. Part of it too, I think, is getting in a hurry. You guys need to block time and say, I've got a quiz today. I'm going to jump on it here. I'm going to block some time out and take care of it. Try to get away from those disturbances. Whatever you're doing on your phone or whatever your device, kind of put that stuff to the side. Stay with it, because some of these are simple. The decimal's in the wrong place. Or you divided 7,200 by 240, and then you put the numbers in the wrong locations as far as the 1 to 30, it's 30 to 1. Take your time. Reference the afternoon videos. Okay, we showed how do you get the transcripts from those videos also. So you got plenty of tools out there to use. I think some people are just, I'm in a rush, I need to get this done. What's in the books is in the books. These 30s, 40s, and 50s and zeros really, really hurt a grade. Okay, Professor B.
Okay. All right, guys, I've got the quiz 4 pulled up here. And we're going to start off with question 1. And I'm not going to change any of the answers or the numbers in it. I'm just going to go by the quiz. It says transformer primary voltage is 19,900, I should say. Secondary voltage is 277. What's the ratio? Somebody figure that out for me.
Well, somebody figure out and let me know how you did it.
Anybody?
You just divide the two, 19,900 into 277.
All right, sounds good. And of course, we allow calculators. So what did you get there?
71.84.
All right. All right, give me the ratio then.
1/71.84.
Right. And this is why I've told you multiple times, I like writing it out on paper. One, for every one of these, I need 71.84 of these.
Okay.
I'm looking at the answer for this student right here. Guess what he put down? 71.84 to 1. That is incorrect. Okay. That's just rushing right there. That's getting in too much of a hurry.
Yep.
Okay.
And
Any
we're going
questions
to,
there?
is this a Ohm's law problem? Anybody?
Good question.
No.
Okay.
No,
Just remember when you use Ohm's law and when you not, when you're going to divide using, as a ratio. Okay, any questions? Question 2. Transformer primary voltage is 4,800. Secondary voltage is 480. Find the ratio to start with. That's the first part. How many amps will be on the secondary side if there are 3 amps on the primary side?
okay, so I think Edric answered the first one last time, how he found the ratio. He took 4,800 and he divided it by 480. What's that answer?
1/10.
1 to 10. Okay, you notice I left myself a little space here to throw those numbers in. When I'm going down in the calculation, what do I need to do?
You need to multiply the two numbers.
Excellent. 3 times 10.
It should give you 30.
Excellent. Answer. Good job. Let me reference and keep up with these. All right. That one was good on that answer.
Okay.
All right.
Guys, you got any questions about how to figure that out?
If you need to check your work here, go backwards. What's 30 divided by 10? I'm going up now.
That'll give you 3.
Excellent. Excellent. There's a check on your work.
Okay.
Perfect.
Hearing no questions, we'll move on to number 3. A service has voltage of 240 volts. The current is at 62 amps. What size transformer is needed for the service?
All right, so we got a clue going on right here. He has given you a voltage number and an amperage number, and you're looking for a what?
What size transformer?
What?
You're looking for a power number. Do we need to reference Ohm's law?
Yes.
Okay,
Yes, sir. You got time to put it together.
there you go. Thank you very much. Thank you, Tristan. So in Ohm's law, it's voltage times amperage equals power. Somebody calculate that out for me, please.
14,880.
All right, 14,880. Now remember here, guys, remember, there's no such thing as a 14,880 transformer.
I'll give
We've
you the
got-
options.
Yep, we got to reference the chart that we provided to you in D2L. What transformer size fits 14,880?
15.
15 kVA. Excellent. Good job.
Questions? Comments?
Yeah.
All right, moving on.
If there's a point in here where you say, well, where did you get that from? Ask.
Ask.
Yeah, ask. Even if you need to push it out and remind. I'm watching remind at the same time.
Okay. Question 4. Okay. Primary voltage is 7,200. Transformers are 50 kVA. What size fuse would a transformer need?
Once again, I'm giving you a power number and a voltage number. Now I'm looking for amperage. So what do we need to do to 50 kVA first to convert it to a power number, wattage?
Turn it into
The
50,000.
ratio.
All right, excellent, 50,000. What's Ohm's law? What's the formula in Ohm's law to determine amps? When I have
Equals.
voltage.
You gotta divide it, don't you?
Excellent, excellent. Somebody's on the ball out there. All right, go ahead and run the math.
Yeah, 7.94.
How much?
How much?
I got 6.94.
6.94. Just cut out a little bit. There is no such thing as a 6.94 fuse as far as the industry is concerned. What's that closest to?
7.
7.
7 amps. Fantastic.
Awesome.
Went through
I
that.
heard, I heard somebody say before we started calculating all this that you got to get your ratio.
That was me. I apologize on that.
That's okay. Just, use your thought process in this. If you're given P and E, and you're looking for I, that's an Ohm's law equation.
Yeah, remember, we got P, I, E, and R. And to help out in the question, to know which direction your mind needs to go, if the question asks for a P, and we're providing, remember, we've got to provide two numbers, and you've got an I and an E, you got to go to the Ohm's law chart. That's how you calculate that out. Any combination of the four. And we're asking, we give you one power. We've got to provide two of the I, E, or the R, two of those three for you to calculate that out. If we give you a voltage over here to the side and another voltage, then we give you an amperage right here, and we're looking for another amperage. I know that's what's 3 times 3 is 90, right? We're not providing you with three different numbers. We're not asking for a power and two others. I hope that didn't send anybody out there for a loop. We've got a voltage, we got an amperage. We're looking for another amperage. That's not three numbers. That's only two. That's where you need to calculate out ratio and then do the math from that. Okay. Professor V, this brings something up. This would be a great question that we would probably hear in the afternoon. Great question, come ask us. And I'll do it with you, Professor V.
Okay.
All right, I'm going to clear this screen. Professor V, you gave me 7,200 and 50 kVA. And you asked for a fuse size. Now here's my question. Do I need to do ratio on this? What would your answer be?
No, sir.
No.
Mhm.
My answer, his probably would be back. Look, we're giving you a wattage number, we're giving you a voltage number, and we're looking for an amperage number. Well, that clue is going to tell you right there, hey, that's Ohm's law.
That's right.
So that's how that works in the afternoon. You still get to do all the math, right? We give you the clue of what direction to head, and then you've got to do the work. So that's a great example right there.
And-
Okay,
and don't forget as well, when you're dividing that 50 kVA by 7,200, that's 50,000, not just 50.
right.
Don't forget it's 50,000 K.
Right, we're converting kVA to wattage, power. And
Right.
another problem I've seen out there a couple of times before, Professor V, is this in the calculator. 7,200 divided by 50,000.
Yeah,
That's backwards,
backwards.
right? Punch it in the calculator is 50,000 first divided by 7,200 second.
Right.
All right, good deal.
Okay. Guys, you got any questions about that? Okay, I hope this is helping you all out. All right, moving on, question 5. All right, primary voltage is 7,200. Secondary voltage is 240. Primary amps are 10. How many amps are on the secondary side? Somebody give me that and work it out in your steps.
First question I'm going to throw out there to Zeb Clemens.
Yes, sir.
Do I need to use Ohm's law here?
Not necessarily, no.
No, you don't need to use it at all. He's giving you a voltage. He's giving you an amperage and looking for another amperage. So that one does not fit. Thank you, Zeb.
Well, and then it's the secondary amp is 300.
Okay, how did you find that?
You take 7,200 and divide it by 240, and you get 30. Then you times 30 by 10, and then you get your secondary amperage.
I'm throwing numbers in as you speak. So he took 7,200 divided by 240. That's 1 to 30.
Right, correct.
And he's going down in his calculation, times 10 times 30. And his answer is 300. Good job, Zeb.
Thank you.
Mhm.
Questions?
Okay.
Guys, and if you'll take the time to write this stuff out, just like you see Professor Shoemaker writing it out, it'll make it a whole lot easier.
Mhm.
Okay. All right, we are on question 6. How much in kVA will a 50 kVA transformer do in short-term overload?
So I've got 50 kVA.
Mhm.
Well, I'm at 50. It looks awful, doesn't it? 50
There you go, that's better.
kVA.
Anybody
Right.
want to say what short-term overload is?
In percentage.
Yep.
150%.
150, right?
Right, we go the maximum here for our calculation. So the maximum it'll do is 150% in overload. Now, certain people have certain ways of doing this. So let's see, Michael or Shaw,
Yes, sir.
what do we do here, buddy? What do you do?
50 times 1.5.
Okay, so you convert the 150% to 1.5. That's moving the decimal place over 2 places. You take your 50 and multiply it by 1.5 in your calculator, and you come out with what?
75 kVA.
5 kVA. Perfect. I've seen some people that have taken that 50 kVA and take half of it, which is the 50%, and then just add it together. Same answer. There's a couple of ways around that. Thank you, Shaw. Good job.
Thank you.
Remember, short-term overload, it's 150% when you're calculating that and fuse overload.
Right.
Okay. Questions? Nope. All right, number 7. All right, guys, a 37.5 kVA transformer has an impedance of 2.6%. What's the true kVA of the transformer?
Okay, so you'll notice on my screen, I put a big old minus right here.
Yeah.
Impedance means to hold back. So I need to take 2.6% of the 37.5 kVA transformer. Ryan Morse. Ryan Morse.
Yes, sir.
What do I need to do here, buddy?
You would do the
And this is your method of doing it. When I've got like a percentage like 2.6, do I need to convert that to regular decimal? Let's go ahead and do that. So I'm going to convert my 2.6 to 0.026. Okay, it's not a percentage anymore now. I moved over 2 decimal places. 1, 2. Since how I moved 2, I got to put a 0 in front right here. All right, based on the previous question, 37.5, I got to take 0.026 away from it. Now, this is where Professor V and I differ a little bit. Professor V takes in
Oh,
his...
wait, I remember. 37,500 minus 0.26%.
In your calculator, correct? That's how you punch it in your calculator?
Yes, sir.
All right, do that for me. Go ahead. 37,500 minus 2.6% in a calculator run. What do you have?
9.74.
No.
No, 9 times 2 is
Wait.
18. So I can
Oh,
make sure.
wait, did I hit that wrong? I think I might have hit the wrong button.
You punched in 0.026.
Right.
2.6%. Okay, 36,525. That would be the true KVA.
All right, excellent. Calculator wise, we don't have to go through all this mumbo jumbo I was doing up here. So, and I like V's method right there. It gave you, it spit out the actual 36 what?
36,525.
Thank
That would
you.
be the true KVA.
Okay, no, listen closely. There's no such thing as a 36,525 kVA. We've got the full number here. How do we convert that to kVA?
Oh, it would just be 36.5.
Excellent. 0.5 kVA, right? We had the full power number right here. In wattage, you took it 10, 100, 1,000, that's the K in kVA, and you convert it back to 36.5 kVA. I can guarantee you, gentlemen, and you saw by this previous test, we threw in some numbers in there that looked exactly like this as an answer. That's not the answer. You got to read the question closely. What is the true kVA? So when you punch this 37.5 minus 2.6% in your calculator, one of the answers is 36,525. Read the full question. We want it in kVA, 36.5. Good job. Ryan.
I had to go use the bathroom earlier. That's why I wasn't responding.
Okay, I hope you, thank you. I hope you washed your hands.
I did.
Okay, fantastic.
You guys got any comments or questions about number 7?
With that question, I think like it might help people. Like you don't have to convert to the full wattage value. You can just operate with the 37.5 and multiply that by 0.026 and then subtract your value from that. And then it would be kVA across the board.
All right, hold on one second. 37.5. And this is calculator punch, right?
Yeah.
Okay, minus.
No, times 0.026.
Hold on, clear. Talk it out to me. 37.5.
37.5 from your problem times 0.026, which is your converted percentage value.
Uh-huh.
And then you'd get 0.975 from that in your calculator.
Uh-huh.
And then you would subtract 0.975 from 37.5.
Okay, hold on. So you can, I just want to make sure everybody's got this. You took your 2.6% and converted it to decimal. You multiplied 37.5 times 0.026, which gave you what?
0.975.
0.975. You took the 37.5 in your calculator and you subtracted 0.975.
Yes, sir.
Which gave you,
36.525 kVA.
okay, same thing. Same juncture. That's why I call on multiple people, and I don't want to stray you from the method that you want to use. If you're using that method, thank you, Riley. If you're using that method and it works for you, fantastic. Fantastic. Keep it up.
Yeah.
All right, Professor V.
Ready? Guys, ready to move on to question 8? All right. Secondary voltage is 240. The amps are 212. What size transformer is needed? What are we looking for?
Uh-huh. Let's see, I'm going to call on somebody here. And P watts. So now we have given you voltage, we have given you amperage, and we're looking for watts. Let me see right here. Eric Bourne.
Yes, sir.
All right. Mr. Bourne, do we need to use Ohm's law here?
I don't know. Whenever I was answering this one kind of stumped me.
Okay, you're breaking up a little bit there. We've given you a voltage. We've given you an amperage, and we're asking for a wattage. Is that a case where we need to use Ohm's law?
Yes.
Okay, thank you very much. All right, so now we just need to reference Ohm's law chart. You guys all should have Ohm's law chart. It's in D2L. Let's see, Eric, Mark Elliott.
Yes, sir.
All right, what is the Ohm's law formula for this question? I'm looking for P. P equals what?
E times I.
E, which is voltage, times I. So let's plug in some numbers. My voltage is 240, my I is 212. Somebody multiply those two together, please.
5880.
Okay, 58 what?
80.
Okay, so P equals 5880. I'm going to reference the question again, just to make sure they got my answer right. What size transformer is needed? Uh-oh. So now he's asking for a KVA. Transformer sizes come in KVAs. 240 times 12 is 58.8. Is that calculation correct?
50,880.
50,000. Thank you. I misheard that. 50,008. So I got a 50. I'm just going to throw those numbers out there. 50,880. Got to reference my chart again. There's no such thing as a 50,880 wattage transformer. What's the closest one to it?
50
50 what?
kVA.
Excellent. 50 kVA. That matches my 50,000 watts. That's close enough to it. Even though it's a little bit over, that's minimal, guys. 50 kVA. That one was kind of long there. Any questions? Once again, I'll emphasize, we gave you a voltage. We gave you an amperage, and we're looking for a wattage, Ohm's law. Two numbers provided, looking for the third. Okay. Professor V.
Yeah. Hearing no questions. Question 9. What is the fuse amp value for a 65 amp fuse in overload?
There's that overload question again. What's the number that we use for overload percentage?
150.
50%. Okay. So let me see. Aaron Ford.
Yes, sir.
All right, talk out your math for me here. What we're going to do?
Okay. Let me think.
The okay, so say you do multiply, so you do 65. Let me look at it. 65 multiplied by 1.5.
1.5. Somebody do this for me also while we're off to the side. That gives you what, Aaron?
Let me get a calculator. 65. 1.5. That'll be 97.5.
97.5. Don't forget, this is in an amperage. All right, so hold that right there. Aaron Staples. Mr. Staples,
Sir?
do this for me. Do you have your calculator ready?
Yeah.
Okay.
Yes.
Take 65 in your calculator and multiply it by 150%.
Equals the same thing.
Excellent.
97.5.
Excellent. So there's just another way of doing it. He converted his 150% to 1.5, totally legal. You punch it in the calculator as the numbers lay. 65 times 150%. Don't forget to put or get the one with the amperage value on it. Excellent, gentlemen, both of you. Good job. All right, clear.
All right. Let's move on to the last question here, and then we'll take a break. Word problem, true, false. All right, a residential customer has its thermostat set to 70 degrees year round. Winter temp average is 35 degrees. Summer temp average 90 degrees. Summer temps are harder on the electrical system than are the winter temps. True or
False.
false?
False.
How'd you get that?
Here. Summer.
It takes more to run during the winter.
How'd you do the math?
Yeah.
I just subtracted the 70 minus the 35.
All right, that equals obviously 35. And 70
And
minus.
then it was only 20
Right,
when you subtract from the other one.
right. So you're having to make up 35 degrees in the winter. You're only having to make up 20 in the summer. So definitely wintertime is more severe on the electrical system than summer. Good job.
Yeah, I'll say that's true because I've been out on calls at night and there'd be so much load on secondary lines, they'll be glowing red and they're pulling so much current.
Yeah, I've seen pad mount transformers that are sitting there that have actually melted the snow and ice and the ground is dry around them. And you can see it. It looks like the element on a stove. You're starting to turn red, paint's peeling off.
That is so true.
Okay.
All right, that's the that was quiz 4. I hope you guys, if you missed anything on that from last week, that you picked it up. Any questions before we go to break?
I'm ready to roll.
Are you ready to roll?
Okay.
All right, gentlemen. Like I said, the exam's going to be in the morning, right, Professor?
Yes, sir.
Okay. All right. What we're going to do is it's only going to be 4 questions, but there's multiple parts to each question. Okay. There's going to be a couple of transformer nameplates similar to what you're seeing on the screen now, but not what you're seeing on the screen now. So I'm going to read through the questions. If you want to do the calculations from the questions from this nameplate, we'll check your answers. Okay, you good with that, Professor Shoemaker?
Absolutely.
Okay. All right. Based on the transformer, go ahead.
Sorry, that was me. Go ahead.
Okay. Based on the transformer that you see there, the nameplate. Okay. What's the ratio?
Okay. So,
Okay.
and I'll give you a little primer right here. There's your KVA. I'm circling it. Your high voltage is 11,000. your low voltage is what?
433.
433. Okay, so now I'm going to go to my screen here. So we got an 11,000 high voltage, and we got a low voltage of 433, and he's asking for ratio.
Yep.
So I'm going to run my calculator, and I'm going to divide, get this a little bit more shaped up on the screen here. I'm going to take 11,000. And what do I need to do next?
Divided by 433.
Thank you very much. 433 equals. Okay, and like we go down to the 10th here. And we need it. Let's everybody show us the solution.
We got 1/25.40.
All right, he's asking for ratio. Excellent. Thank you very much. So I'll go back to the other screen. Right, and this is why I like drawing them out. 1/25.4. Okay, any questions there? Asking for ratio. Take your high voltage, divided by the low voltage. What comes up in your calculator is 25.4. For every one of these, I need 25.4 433s. If you want to check your math, what's 25.4 times 433?
Are you screen sharing your math?
Oh, why did it pause? It paused for some reason. My bad.
Mhm.
It equals 11,000.
11,000. Okay. I don't know why it's only sharing the. I'll fix that. You can carry on. I'll fix this.
So that's part one. Okay, when he gets back with the nameplate, we'll go to part two.
Okay.
Ready?
Yes, sir.
Now, second part to this question is, what is the true KVA after impedance is calculated?
So we need to go back and find the impedance of this transformer.
Mhm.
All right, so we're going to take a close look right here. Percentage impedance voltage, 4.65%. 4.65%. I'll let you know on some nameplates, it has IMP percentage. Not all written out like this, but it's the same thing.
Most of the time they'll have a percent symbol, IMP, IZ, it'll say impedance. There's multiple ways. Just look for that percentage.
So file, new, don't save. All right. So we're asking for the KVA.
True KVA after impedance.
Uh-oh, so I need to bounce back and find out what my KVA was. Huh. KVA was 1,250. So I'm going to write that down. 1,250. My impedance was 4.65. 4.65. Seeing as how there's multiple people doing it different ways, pick on somebody, V.
Would it just be 1.1 kVA? The true kVA?
Let me know
1.1?
your math. Let's figure it out.
So I subtracted 1,250 minus 4.65%.
Okay, hold on. Let me throw a calculator up here. Let me clear this. So you took 1,250 and you minused it by
4.65%.
4.65%. And it gave you this number?
It gave me 1,191.875.
Whoa, how'd I get that wrong? 1,250 minus 4.65 equals. There you go. I keyed it in there wrong. All right, Professor V. Professor V,
Yes, sir.
are you asking for KVA?
I want the true KVA after impedance is calculated, and that number is not correct.
Would 1,191?
Yes,
That is?
1191.87.
All right. So what am I doing wrong here?
You didn't put the percent in for 4.65.
Uh-huh. Go back to my calculator. Let's clear this. 1,250, and you
Yep.
see me punching the numbers, minus 4.65. I'm going to hit the percent key.
Percent equals.
Ha! You got to carry on with that further equals.
Yeah.
Got you. 1,191 KVA.
Mm-hmm.
Excellent. So even I was having a problem there punching it into a calculator. Make sure you follow all the way through.
Yep.
Thank you very much.
But that would also just be like 1.1, right?
Not, oh, good
Not
question.
like it would just be 1.1, right?
1.1 what?
KVA.
No.
No.
Because you did it through the calculator, it remains.
What? Okay, well, I was just wondering, doing the placement thing like we were doing like earlier. It would
Okay.
just be 1.1, right?
To answer your question, no. When you do it through the calculator in that fashion, and Professor V taught me that just earlier in the course here, when you key in 4.65% in the background, it converts that 4.65 and subtracts it from the number for you. So your ending solution is going to be 1,191.8 KVA. It's answered for you.
Okay.
Okay, good job. Good question too.
Mm-hmm.
All right.
Okay. Got one more part to that question. You ready?
Yes, sir.
Guys, you got any other questions about that? Impedance? All right, last part of that question. What will the transformer KVA be in overload?
Oh, excellent. So KVA again, 1,250. Got it on my nameplate. I'm gonna take 1,250. What's the math I need to do here?
Times it by 1.5.
1.5. Okay, you're going that direction, which is fine. Fine and dandy. Clear my calculator out. 1,250 multiplied by 1.5. $1,875. 1,875 KVA.
Sure.
Okay. Thank you very much. Clear. All right.
All right, you want to keep that same transformer chart?
That's good. Yeah, why not?
Okay. All right. Yeah, guys, any questions so far on any of that?
So it's one question with three parts.
Yep. Question 2 has has 4 parts. Okay. All right. All right. Looking at that transformer nameplate, what size fuse is required? What are we looking for?
So what numbers are we going to use to compute the fuse size for it? We need two different ones. We need a voltage and an amperage, correct? I mean, excuse me, voltage and a power. That's what's provided to us.
Yes.
Okay, I've got a power number right here,
It would be
1,250.
you would do the 11,000 divided by the 1,250.
Okay, so you're taking 11,000, which is the high voltage, and you're taking the 1,250. Did you convert that to watts?
I got 8.8 when I did the math.
Okay, did you convert this to watts?
I was just punching in the numbers, like doing the math.
Tell me how you punched them in your calculator. Let's all learn.
I just did 11,000.
Uh-huh.
I did 11,000 divided by 1,250.
11,000 divided by 1,250
Yes, sir.
equals 8.8.
So you would need a 10 amp fuse.
Okay, does everybody agree?
No.
Okay, let's clear this entry here. Let's go back to our name. Oops, sorry. Back to our. All right, so I've got 11,000. We're not working with Ohm's law here yet. We've got a voltage. We've got a kVA. But a kVA is not in Ohm's law chart. What do we need to do to 1,250?
Multiply it by 1,000 to get it into watts.
Right. 1,250. And I need to add 3 zeros. 1,000. Okay, so 1, 2, 3. Okay. 1, 2, 3, comma. 1,250,000 watts. Now I have a watt. All right, run your math again. So we're going to take 1,250,000. Uh-oh. 200 yet?
You would need a 125 amp fuse.
Stand by. Here. 1,250,000 divided by 11,000 equals 113.6. Is everybody coming up with that solution? Who came up with 113.6?
Me.
Okay, I've got Logan muted there because he had some background noise going on. Ethan Johanning. Ethan. Ethan.
Sure.
Ethan. Hunter Campbell.
Yes, sir.
All right, what did you come up with for that solution there?
Are you asking me or are you still asking Ethan?
If your name's Hunter Campbell, I'm asking you.
Okay. I didn't do the math out of my calculator. I was writing it on a piece of paper here.
All right, well, so talk me through it there, buddy. So you took your 11,000, you converted your kVA to watts, which is 1,250,000 watts.
Yep.
And what'd you come up with in your calculator?
113.63.
Excellent. All right. So there's no such thing as a 113.63.
No, sir.
What are you going to go with? So the fuse sizes, if you don't have your chart up, it's in D2L. Your fuse sizes go 80, 100, 125.
So you're gonna go with a 125.
Yeah, I would too, guys, because I'm above the halfway point of 100. 125A would be correct.
Yep.
I did hear that answer earlier. Thank you very much. Okay.
Guys, got any questions about that? Kind of made you think a little bit.
Yep. Don't forget to convert. KVA is not in Ohm's law. We provided you a voltage. We provided you a KVA. And we asked for an amperage. That KVA has got to be changed to watts.
Okay.
Then it fits Ohm's law.
Okay. Questions? Now's the time. All right. Now, what will the fuse amperage be in overload?
Oh, so we're using a 125.
Yep.
All right, we're using the same fuse we just calculated. And he wants to know what it's going to be in overload. What do I need to put here? 125 times what?
1.5.
Excellent. I'm not going to bring up the calculator. You guys go for it.
$187.5.
187.5. There's your answer. All right. That's what we calculated for fuse size. And then you answer the next part of the question. He asked for overload. We converted 150% to 1.5, which gave us our, and then calculated that out. Good job.
What? Okay. All right, throw some numbers out here at you. Using that same nameplate, if there are 100 and let's say if there are 200 amps on the secondary side, how many amps will be on the primary side?
Okay.
What do we have to do first?
Write it out and find your ratio.
Right. So who answered that? Who said that?
Mark?
Me.
All right. What two numbers are you going to use? The high voltage and then what?
The low voltage.
Excellent. Thank you very much. So let's get this going on. The high voltage was 11,000. And the low voltage was 433. Ian tuning. Ian.
Yes, sir.
All right. What's the ratio of 11,000 and 433? That's my high voltage and low voltage. Do you know the math process? What math process am I going to use to find it out?
You're gonna times it.
We'll take 11,000 and divide it by 433. Okay, so I've got 25.4. All right, let's go back to where I'm writing it out. So that's going to be 1 to 25.4. That's how you figure ratio. Professor V, could you state again the question?
I will. If there are 200 amps on the secondary side, how many amps will be on the primary side?
We're going up this time.
We need to divide.
Right, that's fantastic. Divide what by what?
Need to divide our ratio by our secondary amp, right?
Correct. What two numbers are you going to use?
225
25.4.
Excellent. So let's do that. 200. Not all that. 200. You say divide by 25.4. 7.87. Okay. Now I have to refer back to my chart again. Now there's a little bit of thought processes here. Think about it. My
We're just
fuse
looking
size-
for, we're looking for the amps on the primary side.
Right, right.
Yep.
So I took, let me go back to, I took 25.4 and I divided it. I mean, I took 200 divided by 25.4, and that gave me on my calculator 7.87. So we're not looking for fuses, we're just looking for
No,
amp.
we're just looking for amps.
Excellent. So question finished.
Right.
7.87 amps. We're not looking for fuse size, just looking for the amperage number.
Okay.
All right. Any questions there? Every time we ask you for a ratio, take the high voltage, divide it by the low voltage, whatever it is on the transformer. So we took 11,000 and divided it by 433. Every single time you do this, you're always going to have a 1 up top, and whatever this division comes out to, 25.4 at the bottom. That's how you figure ratio. Okay.
I missed the part how you got the 200.
Excuse me?
I missed the part how you got the 200.
That was in the question.
It was given to us.
Right. That was in the question. So let me do this right here. Things that will be provided to you. Obviously, on the nameplate, we had high voltage. On the nameplate, we had low voltage. You got to figure the ratio to find out what the amperage is. This is the big question mark. This is what we were looking for. The question provided, if there are 200 amps on the secondary side, how many amps are on the primary side? The work you had to do, find the ratio, 1 to 25.4. This number was provided. So you did the math, divide that, which gave you your solution of amps. Okay? I mean, think of it. I'm going to clear this one off, Professor B.
Okay.
I'm going to provide you with some numbers here. 7,200 volts. Find the ratio for me. Javier,
Yes, sir.
find the ratio for me. Tell me if I can do it at all.
Well, no, you need two numbers for that.
Excellent, excellent. All right, find the ratio for me now.
1/30.
Excellent, thank you very much. All right, what are the amps on the primary side? Can you do it?
No.
Nope, you gotta have something on the secondary side, all right? Find the amps on the secondary side. Can you do it?
No, you need another number as
Yeah,
well.
exactly, exactly. We have to, in the question, provide a number. You have to take a measurement. Now, if there's 7 here, times 30 equals 210. All right. Be sure to refer back to that question, because these questions are making your mind work. There's multiple things you have to pull from the question to get your calculation. All right, Professor V.
Okay. Last part to the question. What will the secondary amps be when the transformer is at 150% power or kVA?
Ooh, that's different. So I'm going to take, so you got in your question, state that question for me again.
What will the secondary amps be when the transformer is at 150% kVA?
All right. So let's take 1,250 kVA. And you're asking for one number and you're
Yes.
providing two. Let's convert that to watts. $1,250,000. Now I've got a wattage number. My voltage number was 433 because he asked for it on the secondary side. Now I'm just going to do it like normal. I'm going to find out what my amperage is. How do I do that?
Do your ratio.
I've got a wattage number and I've got a voltage number and he's
Multiply.
asking for an amperage number. This is Ohm's law.
Multiply.
No, you need to divide them, right?
Yeah.
Yeah, if you look at your Ohm's law chart, P equals, I equals P divided by E.
Yeah.
P divided by E. So let's try that. Let's clear this entry. See if I can remember my numbers. 1,250,000 divided by 433 equals 2886883. All right, that gives me in my answer right there. I'm going to go over to my paint screen. I'm going to remember 28868. 288.6.8. That gives me the amperage as it stands. What's the other part of your question, Professor B?
All right. Excuse me, guys. What will the secondary amps be when the transformer is at 150% kVA?
Right. Simple right here, guys. Once you figure it out for 100%, what do I need to do with the 288.68? It's at 100% right now.
Times it by 1.5.
Excellent. There you go. 28868. And let's see, times 1.5. Bingo. 4330.25. Answer. That was kind of lengthy. And I had to put my brain to it a little bit.
Mm-hmm.
Does everybody understand that one? If this is what the transformer will do at 100%, we had to figure that out. We had a I equals P over E, so I figured out my normal amperage. All right. What will it do at 150%? It's just the adder to that question times 1.5 equals 4330.25. Any questions there? That was kind of new.
Okay.
Okay.
No questions, no comments.
Nope.
Okay. That was question 2. Okay. Now, question 3. This is not using a nameplate.
Okay.
Okay, you are responding to a trouble call. The customer explains that the transformer is humming very loud. It's a mild day. It's 70 degrees outside. The transformer is feeding 4 medium-sized homes. Okay. Upon initial inspection, the transformer tank is very hot. The transformer size is a 10 kVA. your amp reading is 100.25 amps. Should this transformer be upgraded? If so, to what size?
Okay, do we have a primary voltage there?
No.
Oh, it's feeding a home. Aha,
Yeah.
aha, got it.
Mm-hmm.
What voltage feeds the normal home? Well, I had to think
Mhm.
about that for a moment.
Okay.
Okay. Wow, you're providing me with a wattage.
Yep.
You're providing me with a voltage. And you're asking me if this 100.25 amperage is okay because the transformer is hot. It's working real hard, it sounds like.
Mm-hmm.
So let's do some math. I equals P divided by E again. Let's plug it in. Let's clear this entry. 10,000 divided by my secondary voltage was 240. Uh-oh. 41.6. Ooh. What's this number right now? My answer is 41.6. And the transformer by my readings is doing 100.25. Professor V, your question was, does the transformer need to be changed out?
Yes.
Wow. What do you guys think?
Yes.
Absolutely.
Yes.
All right. What it should be doing is this. What it is doing is 100.25. That's more than double the capacity of the transformer. So it's running a little bit over 200%. Yes, that transformer needs to be changed out. Most definitely.
Okay. What size KVA?
Ooh. A 15? You think a 15 will do it?
I think you'd be all right with a 25.
All right, well, let's work it out a little bit. Let's go work our brains a little bit. So I heard a 15 kVA and our secondary voltage is 240. Now we got to remember this number right here. We want to at least cover 100.25. So I'm going to go back to my calculator. Clear this entry. Let's do 15,000 divided by 240. Uh-oh. 62.5. 100.25. That's not going to make it. So let's try 25. And my secondary voltage is 240. So that's 25,000 watts. Let's punch that in my calculator. Let's clear this entry. 25,000 divided by 240 equals. Bingo, 104.1.
Nice.
100.25. That 25 kVA will fit nicely. Any questions there? You see how I did it? There's another way to do this if you want to use, I did it by all math. What's 41.6 plus 41.6?
Like 83.2, something like that.
83.2. Okay. So I doubled my amperage here. I can also, when you do that, double your kVA size. That 83 still doesn't meet that. What's the next transformer up on the chart?
25.
15, 25. Yeah, 25 will do it. I just went around, the cat's tail on that one. If I double my amperage, that means I double my transformer size. Still does not meet it. 25 definitely will. At an extra 5 kVA. This way, I did it math. Yep, 104.16. Any questions there? Got to read these questions closely. All right, Professor V.
Okay. All right, that was question 3. You guys got any questions about these questions so far?
Questions about the questions?
Questions on the questions. All right.
So will y'all give us that nameplate on the exam?
You
Or like
did.
the numbers that we need? Those are for the earlier problems,
Yeah.
not necessarily that one.
It won't be this nameplate. The exam will have a picture of a nameplate. That is correct.
Okay,
Two
that's all.
different nameplates. Yep.
Okay, sounds good.
Okay. Now, number 4 is going to kind of give your brain a little reprieve here. Name 4 items of PPE, personal protective equipment, that shall be worn while working on a job, not including rubber gloves.
Oh, great. Well, we've done safety videos on this. Let's start at the top.
787 eyeglasses.
All right. So you're saying eyewear. Eyewear. That's a Z87. Eyewear. That's one. How are you going to protect that dome?
Your hard hat.
Excellent.
Hearing protection.
Earring. You wear earrings?
No, hearing protection.
Hearing protection.
And your fire retardant suit
Excellent.
or your clothes or whatever.
Mhm. Professor V, is that a right-in answer?
Yes, it is.
Okay. 4. FR clothing.
Steel-toed boots.
All right. 5. Boots. Okay. Anybody else? Uh-oh. One of these does not belong. I said ask for 4.
Yep.
And you got to look specific to the question. Minimum requirements. Minimum. As soon as you step out of the truck, what do you need to have on?
All 5 of them.
Nope.
Top
You can-
4.
Probably take off hearing protection, couldn't
There
you?
you go. Hearing
Yeah,
protection is
yeah.
needed as an as-needed basis. Okay? I'm glad whoever answered it that you were thinking about it. How do I know when I need to wear hearing protection?
When you
If you-
can't hear the person beside you.
Yeah, can't hear conversation. Okay? But as far as me, as soon as I step out of my fleet, I've got to have safety glasses on, I've got to have a hard hat on, I got to have my FR clothing on, and I've got to have boots on. Now, as things progress, I'm gonna have to put leather gloves on. As things progress and I can't hear anything, I'm gonna put my hearing protection on. These are the minimums. Bang, 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 and bang, when you step onto a job site. Even when you walk in a substation and you're gonna do a visual inspection, you're not gonna do any work at all, you still have to wear these 4 items. Okay, Professor V.
Hey, that's it.
That's it.
That's it. That's going to be the exam.
Mm-hmm. I have to admit, there are questions that are even me, because I don't have it up in front of me right here. I had to re-reference the question multiple times to make sure I was on the right path. I had to do some computations that were not in the question, like figuring out ratios. That question wasn't asked, but I still needed to figure it out.
Yep.
I needed to use Ohm's law. That question wasn't asked, but I still need to figure out. So, you know, these guys, this quiz is going to put your brains to work. When do I need to use a ratio? When do I need to use Ohm's law? Okay. All right, Professor V, anything else you'd like to add?
I was just, when you see this tomorrow, look at the nameplate carefully. Check your high voltages, your low voltages, your KVA, your impedance. All that's going to be on both nameplates.
Right. I do want to show something here to make sure that they get tracking right on this part.
Okay.
Fix that. Fix that. Oh, this is hard to see when you're working on a tablet. I'll write it out. Okay. Your nameplate, and we've talked about this a couple times before. Your nameplate has two voltages for the high voltage and two voltages for the low voltage. All nameplates do this. It's for Delta and Y systems. We'll learn more about those later. When you're looking at the nameplate and you need to find the ratio between the high and the low voltage, it's always this number, the second number, and the full voltage output of the transformer. Okay, this number, 19,000, these are the ones we've been giving you, and the full output of the transformer. This number, 7,200, and the full output of the transformer. That's why we haven't talked ratios of this. What's 34.5 to 240? We haven't talked about those ratios at all. But we have talked about 19.9 and 7,200. Those are the numbers that you're going to use off the nameplate. Okay. I think that should be pretty explanatory, don't you, Professor V?
Yes, sir.
All righty. Okay. Break time?
Oh, let's see. Yes, sir. Yes, sir. It is 9:57.
What do you want to say? 10:10?
10:10.
All right, 10:10. See you guys at
10:10.
10:10. Okay, so gentlemen, that is the review of the previous quiz that we had, plus a review of the exam coming up. Just to emphasize again, the nameplate that you saw for the review is not going to be the nameplate that you're going to get in your exam, and that nameplate picture will be in the exam. So let's talk a little bit about logistics here. How are we going to do this tomorrow morning? Everybody will log into Zoom tomorrow morning and we'll take attendance. Then Professor V and I will be online all morning. Pretty much tomorrow is exam and wrap up.
Yeah.
Of ELW 110. So we will, when I say all morning, we'll be on Zoom all day, won't we?
All day?
Yep. So we'll open the exam up at 8 o'clock tomorrow morning. We'll be on Zoom tomorrow morning to take attendance. If you want to stay in the room, I would highly encourage it. You can mute us. You can mute anybody else. If you want to leave, that's fine. And come back in and ask questions to the entire course of the exam. We will be here. And like before, I mean, guys, use this as a resource. The YouTube video that's going to be put out today, very, very informative. There's a lot of good material in that. So that's a good reference for you guys to study on this afternoon. So 8 o'clock tomorrow morning, check in, start exam. We will be online all day long. While we're sitting here at it and you were away, was there anything that you thought of as far as what we talked about on the exam that you would like to discuss now? Let's see, I'm going to pick on somebody. Bryson Barfield.
Bam.
Yes, sir.
When do I use Ohm's law?
When you're trying to find either the watts, the amps, hold on, I know the rest.
Watts, amps, or volts?
Yeah, volts, and then there's watts, amps, and ohms, right?
Right, ohms and resistance.
Yes, sir.
When we ask a question on a quiz or an exam that's coming up here, do I have to provide you at least two numbers, like a wattage and a voltage?
Yes, sir.
Okay, fantastic. Let's see, Calvin Lloyd.
Yes, sir.
When do I need to use a ratio? When do I need to find out a ratio?
You're trying to, like, say you got a high voltage and you're trying to figure out the low voltage, or you got a low voltage and you want to figure out a high voltage?
You're close, you're very close there. You're going to get a high voltage and a low voltage. Then you're going to get an amperage number, right? Figuring the ratio only, you're going to get a high voltage and a low voltage. Then you need to figure the ratio. Okay. If we progress on and say, well, what is the amperage? You're going to get a high amperage on the high side or a low amperage on the lower side. Then you just use the ratio to compute. Okay. So
Okay.
two voltage numbers, right? Two voltage numbers must be provided.
So we
find
use the
ratio.
voltage. Yeah, we use the voltage ratio to find out the amperage ratio.
Excellent description right there.
Okay.
Okay. All right. That's probably one. Wouldn't you agree, Professor V? It's probably the one that probably trips people up the most.
Yeah.
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 Do I need to use ratio? Do I need to use Ohm's law?
Mm-hmm.
All right. So anything else you'd like to add? Oh, don't forget to reference the chart.
Yeah.
All right. You're going to come up with an answer like 24.35 for amperage. I mean, for a KVA. Well, 23.45 is not in the KVA chart, but a 25 is. Don't forget to reference that chart. Okay. So, when we get down towards the end here, I like talking electricity. This will be coming up in ELW 111. For a good many of the courses here, you guys are going to need to prepare a presentation. Stand by one moment. Who was that?
Me.
Good push.
Yeah.
Yeah, I got that on recording.
Oh, my bad. That wasn't me.
Who was it?
No, it was.
So let me get a screen going over here.
I think that was Riley Jones did that. He's all serious and everything.
Hey, all the time.
All the time.
All right. So you're gonna ELW 111, 112, 211, and 231 in those courses. You're gonna have to provide or create a presentation for each one of those courses. Really simple stuff, to be honest with you. Most of the students, now, if you have PowerPoint on your PC or Mac, by all means, you can use PowerPoint. I find that most of the students that use cell phones use Google Slides. So make an account out there on Google and create something in Google Slides. I have to admit, if I'm using a tablet or a phone, that's probably the most easiest thing to do it on as far as creating it. And I'm going to give you the information for our first one and actually show you an example here in just a moment. So the first presentation, let's go on a share screen here. Share, whiteboard, share. Let's clean this up right here. All right, so your first presentation is going to be called Generation to Meter. That's how you're going to title it. And really what this is going to teach you and what you're going to learn about in the presentation that you're going to create for us is all of the major components that are required. And I'm saying major components that are required for you to get electricity from a generating station to the meter on my house. Okay, so you know what I think I'll do here? I'm gonna swap back and forth. And I'm actually gonna show one that's been pre-existing done. So let me unshare this right here, stop share. Let me get into it's been a long time since I've been in this account.
Yeah.
Search mail, GENERATION. Generation project. Let's pick a name here. Blake Remillard? No.
No. No.
How about Chris Vaughn?
This was probably pretty good, yeah.
Chris is the guy that's making $98 an hour everywhere he goes.
Yeah, man.
All right. So he did his in PowerPoint. With Google Slides. Uh-oh. That gave me a bomb out error. So I'm going to go by it on just on a regular screen. Let me share this screen. I would highly recommend you write down each one of these slides so you know what you're going to have to include on your slide. It's going to require a description and a photograph of what we're talking about. Screen 4, share. Let me know when this comes up, Professor V.
There it is.
Okay, so my first slide, and this is, I kind of like the way he did it here. Prettier is better. All right, his first slide is just his opening slide, generation to meter. He's got a meter in it. And I would, when you do your searches in Google, I'll just throw out this question. You go to Google and you type in meter, what's going to come up? Let's do it. Go over here to Google. Meter. Images. Oh, wow. Got lucky here, found one.
Yeah.
All right. Be a little bit more specific. Utility. Electric. Meter. Bingo. All over the place. Look at that. Any one of those pictures, a safe picture of one of those, and then you got the picture that you need. So be a little bit more specific in your slide. And he's got the meter in the front for his picture. In the background, he's got a generating station. So he's got generation to meter all in one slide. Slide 2. Might need to make this a little bit bigger. There you go. A generating station. And he's got a photograph of a generating station. Make sure, just like in your Google search, you're going to put utility electric generating station. A power station, also referred to as a generating station, power plant, and powerhouse, or generating plant, is an industrial facility for the generation of electric power. Most power stations contain one or more generators. A generator is a rotating machine that converts mechanical power to electrical power. The relative motion between the magnetic field and the conductor creates an electrical current. Now we're looking at this right here. And you probably learned this in college. I mean, in high school. What's plagiarism?
Stealing somebody else's work.
Stealing somebody else's work or getting some information off the internet, right? Copy paste. I can guarantee you that's a little bit of copy paste from Chris, but he does include a little bit more description in areas and stuff. Am I going to mark you off for plagiarism?
I don't think so, but probably most likely.
Yeah, I'm not gonna mark you off for plagiarism. If you go out on the internet and you find a description for generating station and it fits what a generating station does, I'm okay with it as long as you know what you plagiarized. Be aware. If I find something in this generating station, and we've seen these how many times, Professor Vic? Hundreds. We've seen 100 of these presentations, and I ask you a question. Well, what do you mean most power stations contain one or more generators? If I ask you that question, you don't know the answer. You better know your material that you're using. All right? I'm going to come back at you. When I say a power station, is that also to refer to as a generating station? And you say, well, no, you better have your answer correct. You can copy paste from the internet. I'm okay with it. Know what you're copying and pasting. That is critical. Okay, so that's a good description of the generating station. Next slide. Now we talked about step down transformers before when we used 7200 and 240. A generating has what they call a step up transformer. You'll notice the generating station in this photograph is right behind it. Then right outside the building, they have a step up transformer. Can anybody tell me what a step up transformer does?
Increases power.
Increases. Be careful on your answer right there. A step down transformer steps down the voltage. We had that on remind. What does a step up transformer do? You had it right.
Voltage.
Voltage, there you go. Steps up the voltage. Make sure you get your description right from that. Once electrical current leaves the generators that's inside the station, it moves to the step up transformer. The purpose of a step up transformer is to take the voltage coming out of the generators and convert it to a much higher voltage. 7,200 volts into the transformer stepped up to 134,000 volts to be sent out. There's a reason behind this. You'll notice the size of the insulators and how big all of this material and the potential high voltage is, just the danger of it. I can't house that in my generating station. It's just way too much, one, money, and two is that voltage at that high of a level inside my building here is just not easy to transport. So I'm going to take a lower voltage out of the generating station and then step it up outside of this generating station to a higher voltage. That's the purpose of it. I want to step it up. Switch yard. So it leaves a step up transformer and it goes to a switch yard. Very good picture of one right here. These are commonly located directly adjacent to the nearby power station. Switch yards are simply switching stations where different connections can be made between different transmission lines. So one generator in a station to one step up transformer just doesn't go out on one transmission line. It doesn't go out on one line. It'll go to a switch yard first, and it can go multiple directions. It's like a train station for electricity. It routes it in different directions. That's the purpose of a switch yard. Good picture of one too. Excuse me. All right, once it leaves the switch yard, we are now going to transmit electricity. That's why we call it transmission. Transmission lines are the big high voltage lines that carry electricity over, and this is vitally important, long distances, such as from a power station to a city or from a grid to a city. They are generally high voltage and are placed on physically tall structures. Great picture right here. You'll notice when we're out at our field, when you look out towards Highway 501, we've got some power lines that are lower. Those are distribution voltages. Those big steel poles, brown poles that you see, those are transmission voltages. Big thing that's in the description right here, transmission voltages are able to go long distances. That's why they call it transmission. We're transmitting power, transmitting voltage. All right. Along the path after transmission and along the path of it, we're going to put a substation. The substation is between the generating station and consumer. Electric power may flow through several substations at different voltage levels. A substation may include transformers to change the voltage levels between the high transmission voltages and the lower distribution voltages, or at the interconnection of two different transmission voltages. So you can actually take transmission voltages and transform them down to lower transmission voltages, or you can take transmission voltages and step them down to distribution voltages. We'll get to distribution here in just a second. So a substation vitally has a transformer in it, a huge one, to step down voltages. Bus bar. A bus bar is an electrical bus bar defined as a conductor or a group of conductor used for collecting power from the incoming feeders and distributes them to the outgoing feeders. In other words, it is a type of electrical junction in which all the incoming and outgoing voltage and current meets. Bus bars, and we got another picture up here up front. Excuse me, it was at a switch yard. You'll notice in this picture right here, it's just loaded down with bus bars. All that aluminum shiny part you see is bus bar. And down here also is bus bar. The benefit of using bus bar, both instances are in substations. Well, that's a switch yard, or in a switch yard or a substation, is I'm able to carry very, very high current. It's a solid piece of metal, and we're not using conductor here. It's a lot more expensive, but we're able to put high current on these right here and use them to be able to distribute high currents. We can't do that on power lines, obviously. We got to use some kind of like aluminum wire. Inside the substation, there is a substation breaker. Substations generally have switching protection and control equipment and transformers. In a large substation, circuit breakers are used to interrupt any short circuits or overload currents that may occur on a network. Anybody ever have a breaker trip in your house?
Yes, sir.
Yeah, how about a fuse blow in your car?
Yes, sir.
Yeah, sure. That's the purpose of a circuit breaker, a substation breaker. If there's something going wrong with my power lines and I have a short circuit on my power line, a substation breaker will do its job. It'll open. Feeder line. Now we've left the substation. This is in the substation. Now we're coming out of the substation. This is more terminology. You're going to need to know this from the slide. Professor V, are you here?
Yes, I am.
All right. Santee Cooper calls the lines that leave a substation feeder line. What do you
Yes.
call it, Professor V?
Same thing, feeder.
I've heard some other companies call them main line.
Mm-hmm.
That's
Trunk line.
exactly I've heard. Have you heard any other ones like that, Professor V?
I've heard them called different places a trunk line and then branches, you know.
Yep. Okay. So feeder line is my terminology. If you use main line here, that's fine. Feeder line is the line or main line, look at that in the description, is the power line that comes from the substation to carry current to the consumer. So this comes out of the substation, just like at our school here. It's going up and down 501. It's at a lower voltage level. And you'll notice here, he's got his picture of feeder line and right below it, a transformer for a home. Okay. Fused tap. Now these get into the more difficult slides to find. When you search for it, make sure you search for utility or power company fused tap. A fused tap is a device on an attached power pole or cross arm that is connected to the power running to a residence or multiple residences, allowing you to de-energize that section. So I can come off my main line that's on top, go through a fuse that you see I'm cursoring over at here, and go to another line that's fused. Remember the substation breaker we had? It's like the breaker in your house. That protects our feeder lines in case we have a short circuit. When we start tapping off our feeder lines and we need to go down just a small street, do I want protection on that too? Yes or no?
Yes.
Yeah, right. So I want protection down that short portion of street too, but I don't want to take out the entire feeder line. If there's a short circuit on this line, then the fuse will blow. So it's just another protective device for a line. Okay, and a fuse. I think it would probably help you out here if you put in your description fused tap line in your description right here. Okay. Solid tap. Now this is really not the picture that I want to see. I'll show you a picture in a moment. Here's a fuse tap. A solid tap, I'm going to go back to this picture right here. I don't put a switch or a fuse in it. I connect the wire directly from one wire to the feeder side. No fuse. All right. Not really this much anymore. You will see them out there in the world. You're going to run into them, but not really used that much anymore, especially on new installations. I want to have some type of protection if something happens on my tap line. If I have a solid tap and something gets on my tap line, it's going to take the entire feeder out. We don't want to do that. Remind me to go back and see if I can find a solid tap, Professor V.
Yeah.
All right, transformer. Here we go. This is what we've been working with thus far. Transformer in the distribution side is used to step down voltage so it can be usable level for the consumer. Example. Well, here you go. We've been saying it a ton of times. 7,200 volts into the transformer down to 240 volts. Perfect description. And he's got a picture of a transformer. Secondary line. I might run to another pane or something here. Secondary line. Secondary line is what is wheat. All right, secondary line is what runs out of the transformer to the consumer. That is not correct. So let me go ahead and get started right here. Where was I? Paint. And I'll start drawing. So I'm going to start draw a pole right here. And I'm going to put a transformer on it. I have a primary voltage going in and a secondary voltage coming out. All right, now I'll put another pole down here. That is just the pole. Secondary voltage coming out of the transformer and the line going to the next pole, that is a secondary line. Secondary lines go from structure to structure. When I say structure, pole to pole on overhead, that is a secondary line. Okay, so everybody understand that? Secondary voltage out of the transformer, it attaches to this pole, goes over to the next pole, secondary line. It's got to go from one of my poles to another one of my poles. New. Let's save, shrink that down. Service line. Service line is a line that runs and ties it in directly to the meter. 100% I agree. So let's do this again. Pole. Let's do 2 poles. Pole. My transformer again. Primary voltage in. All right, here's my little Adobe over here. And I'm going to put another Adobe over here. And a little meter on the side. I'm going to come up secondary voltages from here. Then I'm going to go directly to the meter. I'm going to come out with a secondary voltage over here and go to the meter at the house. So by his description, service line is a line that runs and ties in directly to the meter, and his picture shows it. The lines that you see come up at the top of this pipe, it's a perfect picture right there, and he's actually showing a meter too. Okay? This, because it goes between structure 1 and structure 2, that's a secondary line. We've already determined that. Everything that goes from the pole to the meter is the service line. Is this a service line?
Yes.
Sure is. Goes from the transformer pole to the meter. Perfect. Service line. That's the difference between the two. And you will need to know these when you start working out there and you tell one of your coworkers, yeah, I've got a secondary line that's down. Well, which one? This one, or this one? 1, 2, or 3?
3.
3, exactly. Well, the service line is down to house number 2. Where do I need to go?
Number 2.
There you go. You guys got it. Got it. Okay. And last but not least is the meter. The meter is a device attached to the home or directly next to the home, showing how much energy is being used in the home. Great description. All right, so let me run these here real quick if you're noting these down on paper. First, let's see.
I sent you a link in Zoom chat that's got a picture of a solid tap.
Thank you very much. All right, first, 15 slides in total. That includes an opening slide. So there's 14 pieces of equipment. Okay, and he's got 15 with his opening slide. If you want, I'm going to go through these quickly. Required slides: generating station, step-up transformer, switch yard, transmission, substation, bus bar, substation breaker, feeder line, fuse tap, solid tap, transformer, secondary line, service line, meter. Let me shrink this down and get over here what Professor V is talking about. Chat. Oh, let's see what happens here. Bingo.
There you go.
Right straight to it. Thank you. All right. Get my mouse back over here. Let's see, control.